In this video, we're going to learn how to write some polynomial functions if we're given some information, like what the zeros are and the degree of the polynomial is. We're also going to graph some polynomial functions given the function. So here's some problems from your book. It says in these problems, form a polynomial function whose real zeros and degree are given. Answers will vary depending on the choice of the leading coefficient. So I'm going to do problems 44 and 50. So problem 44 says the zeros are -2, 2, 3, and we want the degree of this polynomial to be equal to 3. Okay, so a polynomial function is going to look like a n x to the n plus a n minus 1 x to the n minus 1 all the way to a1x plus a0. But we can write it in a factored form. In fact, some of the problems we've been looking at were in a factored form. And the factored form I'm going to go with is I'm going to put a number out here, which is actually going to be that leading coefficient, an. And then I'm going to do x minus one of the roots to a certain degree, then x minus another root, and x minus another root. So here, let me just write it like this. So k1, k2, k3 are roots. And of course, if you have more roots, see my problem has 3 roots, but if you have more, then you would want to put more roots out, like x minus k to the k4th and so on. And these ri's are our multiplicities. Okay, so for us, we have a -2 for a root. So right here, I'm going to put +2. Then we have a 2 for a root and a 3 for a root. Okay, we want the degree of this polynomial to be 3, which means each one of these powers has to be 1. Now we don't have to write the 1. Usually we don't write the 1, but I'm just going to do it right now so we can understand the powers here. Because here we're getting x to the first times x to the first, x to the first. So when we expand this, we're going to get an x cubed. And so then we would have a polynomial of degree 3. For this leading coefficient, we need to pick a number for that. And you can choose anything you want, 1, 2, -5.5. Because here, all we want to do is just find something with these real zeros and this degree. So I'm just going to stick a 5 in the front. So this would be an example of a polynomial function that has these 3 zeros, -2, 2, and 3, and this particular degree. Let's try number 50. We want the zeros to be -2, but with a multiplicity of 2. We want 4 to be a 0 with multiplicity 1, and we want the degree to be 3. So again, I'm going to write it in a factored form. So I have 2 zeros, so I'm going to have a 0 here and a 0 here. So my 0, one of them, is -2. So now we're going to make this a +2. And we want the multiplicity to be 2. So I'm going to put 2 here. And then we also have a 0 of 4. So I'm going to put -4 here. And the multiplicity on this one is 1. Now you can see if we expand this, I would get an x squared term here and an x term. And when I multiply them, I will get an x cubed. So that will be the degree because that will be the largest power on an x. And then I just choose something for an. I'm not restricted, so let's put something like -1/25. Just something in the front like that. Okay, let's move on. In these problems, we want to find a polynomial function with the given zeros that pass through the given point. The zeros I have are -2, 0, and 2. Now we're going to assume that this polynomial function only has real zeros. Now there are polynomial functions with complex zeros, and since they're not given here, we're just going to pretend like they don't exist, because if they're not given here, then we're going to assume this polynomial function doesn't have complex zeros. These are the only zeros. So if these are the only zeros, this function is going to look like this. A(n) x minus k1 to the r1, x minus k2 to the r2, x minus k3 to the r3. Where k1, k2, and k3 are these zeros that we have. And this r1, r2, and r3, well, they don't tell us what the multiplicity is for each one of these. It just says find the polynomial with this given zeros and passes through this given point. So we can actually choose the multiplicities we want. And the easiest thing to choose is to make them all 1. Now you can make them whatever you want. You can make a 3, a 7, and 8, because we're not restricted. And this k1, this k2, and this k3, so this is going to be +2, -0, and -2. I'm just plugging in the zeros here. Again, if we had more zeros like this one here, I would need 4 linear factors. Okay, and there's a reason why I'm making this a 1, a 1, and a 1. And that's because I also want to go through this point, and I want to make my algebra as easy to manipulate as possible. So the first thing I'm going to do is I'm going to clean this up, because x minus 0 is the same thing as x. So the polynomial function we can work with is some coefficient times x plus 2 times x minus 2. And what I'm going to do, I'm actually going to expand this a little bit. This is a(n)x. This is the difference of squares here. So this is x squared minus 4 if you multiply this out. Now you don't have to do this piece, but I can also send in this x. I'm going to leave it just like this. Now I want this polynomial function. I'm not just going to choose anything for this coefficient, because I specifically want it to go through this point, -416. So when we plug in -4 for our x, we're going to plug it into everywhere we see an x, and we can plug it into this one or this one. I just try to simplify it a little bit. What we want to get is 16 here, and that's going to help us choose the right a(n). So I'm going to put 16 here because that is the y value, and then I'm going to plug in -4 for x, so I get a sub n times -4 times -4 squared minus 4, and what I'll get is 16 is equal to a sub n times -4. This is 16, subtract 4. So we get 16 is equal to a sub n times -4, and then this is times 12. So 16 is a sub n times -48. So the right a sub n would be -16/48, because I'm dividing both sides by -48. And we can simplify this. Let me pull out a calculator. I know that, let's see, it's 48 divided by 8. Yeah. So let's divide the top and the bottom. Maybe, let's see if it goes, so both are divisible by 16. So if we divide the top and the bottom by 16, I get -1/3. So this is the correct a sub n for my particular polynomial. So my polynomial, if I plug in -1/3 into here, which that's what I'm going to do, right here. Of course, you can plug it into this form as well, but this form is really nice because we can see all of the factors. We are guaranteed to go through this point, and we have these specific zeros. The other problems are similar. So like on number 56, you can see you're going to have these 3 zeros, and they all have multiplicity of 2. And you would do something similar to this one. So you're going to have 3 zeros, so you'd have these 3 linear terms. You'd put 2, 2, and 2 here. And then you would need to figure out a sub n. And to do that, you would plug in 1 for x and get negative 48 on this side. All right, we are ready to start graphing polynomial functions. So here's a summary that's coming from your book of how to analyze and graph polynomial functions. So what you're going to be given in the next few problems is you're going to be given a function. I'm going to ask you to determine a lot of information about it, but the ultimate goal is to graph it. And what you want to do to graph is the first thing is you want to determine the end behavior of the graph. And how you're going to do that is you're going to find the power function that is related to that graph. And when you find the power function, that's going to tell you the end behavior of the graph. And you got to look at that leading coefficient. And if it's negative, it's going to tell you if your ends are pointing up or they're pointing down, or if one's going up and one's going down, and so on. And we'll go through this when we graph. The second step that's going to help you draw a polynomial function is to find the x and the y intercepts of the graph. So when you find the x-intercepts, you want to figure out if you're touching or crossing the x-axis at those x-intercepts, and you're looking at the multiplicities. So you're going to figure out if you touch or cross the x-axis when you find these roots here, which the roots are the x-intercepts. And that's step 3. So step 2 was to find the x and y intercepts, and then step 3 is to figure out if you touch and cross the x-axis using the multiplicity. So determine the zeros of the function and their multiplicity. Use this information to determine whether the graph crosses or touches the x-axis at each x-intercept. So since that's already written here, we don't need to write it again. Step 4 is you want to determine the maximum number of turning points on the graph. And then for step 5, you want to use the information in step 1 through 4 to draw a complete graph of the function. And to help establish the y-axis scale, you want to find some additional points on the graph. Okay, so that's a lot of information. We're going to do some examples. Here I've chosen 3 examples that I would like to do with you. So for problems 57 through 68, again, this is problems from your book. It says for each polynomial function, you want to list each real zero and its multiplicity. Then you want to determine whether the graph crosses or touches the x-axis at each x-intercept. Then determine the maximum number of turning points on the graph. Excuse me. And then determine the end behavior. That is, find the power function that the graph of f resembles for large values. And actually, we're going to have a part E here, which is not part of the homework problems, but we want to graph the polynomial function. And we're going to do problem 58 first. So we have f of x is equal to 4x plus 4 times x plus 3 cubed. We need to draw the x and y axis here. So I'm going to try to draw a straight line. Let's erase this one and try again. Okay, that's pretty good. And maybe we can even make it a little bit smaller so it's not so big. And if we need to make it bigger, we will. Okay. So we want to ultimately graph this. First part to do that is let's list each real zero and its multiplicity. So looking at this, you can see that -4 is a 0. So let me write it like this. Our zeros are x is equal to -4 and x is equal to -3. Again, to find the zeros, you set this function equal to 0 and then you solve for x. So you would get x is equal to -4. In fact, you could just plug this in, you can see you get 0. The multiplicity, I'm going to abbreviate it to just m. The multiplicity of this factor is 1 because that's the power here. And the multiplicity here is 3. From there, I can go ahead and say that I am going to cross the x-axis for both of these, because this is both of these are odd numbers. Okay. So that gets rid of the first part. And the second part. And why don't we go ahead and graph these? So 1, 2, 3, and just some extra dots here. We're going to put a dot at, sorry, we have negatives for the 0, so let's go this way. At -4, we should have a dot. And also at -3. Be careful not to get your multiplicities confused with your zeros. Okay, and we're going to cross the x-axis at both of these. So we have some options here. We can go down like this, and then eventually we'll have to go up, or we can go up and then go down here. But let's see what happens the further we go along with this problem. Now we want to determine the maximum number of turning points on the graph. To do that, we need to figure out the degree of this function. So let's put right here the degree. So notice if we expanded this, here we'll have an x term. And here, if we expanded that, we'd get an x cubed. And then when we multiplied it all together, we're going to get an x to the 4th term and some other stuff, but all the other stuff is going to have powers that are less than 4. So the degree is 4. And notice that we also have this number 4 on the outside. So that leading term will have a coefficient of 4. So the degree is 4, and also the leading coefficient is 4. Okay, since the degree is 4, that tells us that we can have a max of 3 turning points. So we're going to make some turns in our graph, but the maximum number of turns we can make is 3. The next piece is to, so after we've done this, determine the maximum number of turning points. We want to determine the end behavior. And how we do that is we look at the power function. So the power function goes with this leading term. So y is equal to 4x to the 4th is the power function that's related to this graph. And notice that this has an even power, and this number in the front is positive, which tells us that we're going to look like, at least on the ends, like a parabola. Okay, so what's going to happen? I'm going to give you an idea of what I think is going to happen, and we're going to make a sketch, and then we're going to check it against some kind of graphing software. So this is what I think is going to happen. Since we're going up like this on the sides, the place we're going to have an issue is right around here. We know we're going to have to be going up on both sides, so we're going to, excuse me, we're going to go down. And then here, at some point, we have to cross this, because that's what we found. We have to cross the x-axis. Now, we can make a turning point right here and go up like this. This would be just a regular looking, kind of like a parabola. And here I've only made one turning point. Okay, so that's one option. Another option is we could make some kind of turning point, maybe one around here. But if I do that, I've already got 2. And then something like this. And that's an option. So that'd be 1, 2, because I have to come down and go through this. So that's something we could see. We could also see that on this side. So we could possibly have something like turning point 1, and then like that. That's an option. And we could even have maybe something like This goes down here. We have to go through this. So maybe we get a turning point down here. So something like that. So our graph's going to look something similar. Some things we can do is we could try to figure out the y-intercept. And well, we definitely know we have something going on down here. Okay, so let's find a few extra points. So if we plug in, let's find the y-intercept. That means you plug in 0 for x, and if you do that, you'll get 4 times 0 plus 4 to the first times 0 plus 3 cubed, and we'll get 4 times 3 cubed, which is really big. It's 16 times 27. So this is going to be way up here. Let's see, I don't think at this moment we can do anything else to graph this. So we've kind of sketched something. We know that it could, let me remind you, we could have had just one turning point. We have to go through these, so I expect our graph to look something similar to this. And we could have a turning point here, and we could have a turning point somewhere around here. To actually find where we have these turning points, you'll learn in pre-calculus how to take, sorry, not pre-calculus, in calculus you'll learn how to take derivatives. And these derivatives will tell you where you have the minimum and the maximum. But at this point, this is about all the information we can obtain. We can find a bunch of points to give us a better idea, but at least we know sort of what the graph is going to look like. We know it could have one turning point or 3. And we know that this is going up here and this is going up. So let's see what the actual graph looks like. I am going to pull up some graphing software. So give me just a second. And again, remember that the idea is to sketch a graph. So we don't have to be perfect with this. Okay. And I'm going to zoom in a little bit, and now I'm going to share my screen. Okay. So what you should see is a graph of this function, 4x plus 4, x plus 3 cubed. And let's see what we have. We're going up on the sides like we expected. We go through both of these points, and look, we have one turning point. Here we have something interesting called a point of inflection, but it is not a turning point. So we go down like this, we get pretty close to this point, and then we go back up. Now, something we could do to get a better picture of our graph is to plug in points. So we could plug in something like -5 and plug it into your function. Points that you would really want to plug in is things between the roots. So if you had plugged in something, let's say you plugged in -3.7 into your function, you get this point here, and then maybe like -3.6, and you'd get another point here. That would kind of tell you that you're having some kind of turning point, because it's going to have to go down and back up. And then if you plug in stuff really close to -3, between -3.5 and 3, you're going to get close to that x-axis, so you can see that it's kind of flattening out. And then anything past that root here, you'll see that you're going up. Okay, so let me stop sharing this and switch back to this right here. So I guess we ended up with something that looked like this. Okay, let's try another problem. The next problem we're going to work on is 62. Okay, so let me copy this problem here. It says f of x is x minus 1/3 squared times x minus 1 cubed. Okay, what do we need to do? We need to find the zeros. So the zeros for this function are x is equal to 1/3, and this has a multiplicity of 2, and x is equal to 1, and it has a multiplicity of 1. That tells us that we're going to touch this x intercept, and we're going to cross this one because of the multiplicities. Okay, we need to determine the maximum number of turning points. Well, if we expanded this, we would get f of x is equal to, notice that you'll get an x cubed and an x squared, and if you multiply those together, you get an x to the 5th, plus some other stuff, but this stuff would have smaller numbers for the powers, and the leading coefficient here is 1. So the power function that goes with this function is just y is equal to x to the 5th. And remember that this odd number tells us that we're going to look something like an x cubed graph. We also know that because the degree is 5, we're going to have max of 4 turning points. Okay, so let's try to give an idea of the sketch of the graph. So we're going through 1/3. So here is 1/3. Let's put 1 about right here. So this is 1. We're going to put 2 dots here. And then we know that we touch at 1/3. So our options here are is that we touch like this or we touch like this. But how do we figure out which one we have? Well, we're going to look at the end behavior. We know that at this end we should be going up, and at this end we should be going down. And it's right where the roots are that we're going to have some interesting stuff happen. So because this 1 is further to the right than this 1/3, and we're going to have to cross this, what's going to happen is we're going to go down. We might have some kind of bump here, but we're going to cross through this, and then we're going to have to turn and go back towards this one. And since we touch it, we only touch it like that. So it's not possible for us to have touch it up here because we have to cross here, and we can't cross anywhere else, otherwise it would be a root. So the graph would look something like this. Now here I have 2 turning points from what I've drawn. I can have a maximum of 4 turning points. So what could happen is I might have another turning point somewhere around here. So I could have something like this. That would be 1, 2, 3, 4. That would be 4 turning points. Or I could have done that turning point, those 2 turning points up here, or maybe even right here. But the overall look of this is like this. Now I'm going to check this against some graphing software. So let me write it in, let me put this function in. And I'm going to try to zoom out and see what we have here. I'm going to share my screen. Okay, what you should see is a graph, and notice that it does look like, so here's the function, as you can see, y is equal to this, which is what we had, and look, it does look like x cubed. Now, if we zoom in, right here, it looks like it's kind of flat, but it depends because all of this stuff is really close to 0. It might not be extremely flat. It's kind of hard to see, But if you look close, you see at 1/3, which is right about here, we're touching because we're going up. And then we touch it here, and then we kind of go back down like we expected before. And then at the point 1, you can see right here, let me even zoom into here. It's really close to this line, so it's hard to tell, but you're going to cross right here, and then you're going to keep going upwards. So you're going to be increasing from there on. Okay, so we've done 2 problems. Let's do another one. Here I have problem 66 circled. So we have f of x is -2 x squared plus 3 cubed. Okay. This one's interesting because this is not factorable, which tells you that you're going to have 2 complex roots. So let's talk about this. I can't factor this any further because let's try to factor it, right? X squared plus 3 is equal to 0. If you move the 3 to the other side, you get x squared is equal to -3. And then when you take the square root, you get a negative under the square root, which means you have an imaginary root. Okay? On the real line, we can't draw imaginary roots. So that tells us that we're not going to cross the x-axis. Okay, so I'm going to write that here. We have no real roots. So we do not touch or cross the x-axis. Well, how is that even possible? Well, think about it. We've had parabolas before that didn't touch or cross the x-axis. In fact, if your degree is even, this is possible. Notice that the degree of this function, well, we have an x squared, and then if we cube this, we're going to get an x to the 6. So the power function that corresponds to this is y is equal to -2 x to the 6 because of this -2 on the outside. So we're going to have like a parabola pointing downward. So it is possible. If you have an odd power, you're always going to have at least one root because it's going to have to cross the x-axis, because remember it's going to look like x cubed. Okay, so let's see what we can do as far as graphing this. Since the power function looks like this, I know that we're going downward. The graph will look, now I don't know exactly where it is at this moment, but I know it's going to look something like this. And it could have 5 turning points. It has a max of 5 turning points. Now, to get an idea of where this thing is, one thing I can do is plot points, and the easiest point to find is the y-intercept. So if we plug in 0, let's see what we get. So f of 0 is -2 times 3 cubed. That's 27 times -2, which I think is -54. So that's way down here. So we're going to be going through a point way down here. Now, I really don't know. I'd have to draw more, plot more points, and I don't want to do that because I don't think that is good for us. We might have something like this. 1, 2, 3, 4, 5. You can see that I have 5 turning points. This might be over here some. We might just have 1 turning point. But the structure of this graph, some things we do know for sure, is that it's going to be below this x-axis and that it's pointing down. So let's graph this on some graphing software. So -2 x squared plus 3 cubed. Okay, so this one is not very pretty. Let me also put it in a different graphing calculator. Maybe it'll give me a better idea here what it looks like, and I'll show you both. Okay, so I'm going to share my screen. So this is what I got. As you can see, if we zoom out, oh, this is a horrible graph because you really can't see what's going on. It almost looks like a straight line. But if you zoom in and around this area, you can see that you have two lines here. So it looks like almost like a parabola that's really, really skinny. But you can tell that it's not crossing this x-axis. Let me switch over to some better graphing software. So I'm going to make sure that you can see this. Here, they've changed the axes, like the width of the axes. You can see they're going from 0 to 0.5 here, and 0 to negative 0.5. And then here is from 0 to negative 60. So they've like scrunched in all these numbers in order for you to see it. And it looks almost like a regular parabola. So we only have one turning point for this actual graph. Okay. Let's go back to our OneNote here. Okay. So it turned out that this graph looked more like this. Okay, let's move on. So I think we did all the problems I wanted to do here. And I think, yes, now we're ready to move on to something a little more complicated, which I said in a few videos before, that we wanted to graph polynomial functions, and the ultimate goal was to have it look like this general form, as you can see. This negative x to the fifth minus x to the fourth plus x cubed plus x squared, stuff like this, where it's not factored. So I'm going to do problems 114 and 118. I'm going to show you all you need to do for this. And what you need to do is factor it, if possible. And then when you have it in a factored form, then you can try to graph this. Okay, so 114, we have the function x minus x cubed. So we want to graph this. We want to analyze it. So what I'm going to do first is I'm going to put this leading term in the front. So I'm going to rearrange this to negative x cubed plus x. Just move this in the front here. And then I'm going to put over here the power function. Y is equal to negative x cubed. That's the power function, which tells us that we are looking like x cubed, but flipped because of the negative. The next thing I'm going to do is I'm going to find the roots. And how I'm going to do that is I'm going to factor. So notice that the greatest common factor here is a negative x. We can take that out. And we'll get x squared minus 1. And then I can factor this. This is negative x, x minus 1, x plus 1. So our roots are x is equal to 1, x is equal to negative 1, and also this one in the front, x is equal to 0. And you can see for each one of these roots, we have a multiplicity of 1, which tells us we're going to cross. So let me draw this. I'm going to put these three numbers here. This is negative 1, 0, and 1. And we're going to cross each one of these because this is multiplicity 1. I also know that we're going up like this and down like this. So we can try to sketch this already because we can go down through here, and at some point we need to make a turn and then go down through this one. So here's a sketch of the graph. How many turning points do I have? I have 1, 2. And notice that that's the maximum number of turning points I can have. Because this is x cubed, that's the degree of the polynomial, and the maximum number of turning points is 2. So your graph has to look like this. You can see that you can't go through these 3 points with less turning points. There's no way to cross like this. In order to cross this one, and cross this one, and cross this one, we have to have 2 turning points. It's going to look just like this. Although this hump right here may go further down, and this one may go further up. So let me graph it so you can see it. X minus x cubed. So let's go here. Make sure you can see. My screen. Okay, let me zoom out. Okay, this is hard to see on this one. So let me move over to Wolfram alpha. And we're going to graph y is equal to x minus x cubed. And you can see that this looks just like what I drew. You can see that we have to go down and then through 0 and then back up. Okay, let's go back to the OneNote. And I'm just going to start you on 118. I'm not going to do this full problem. I feel like we have enough information to graph this. So let's just write it out, what we need to do. So for 118, we have f of x is 4x cubed plus 10x squared minus 4x minus 10. So we ask ourselves, what's the degree of this function? The degree is 3. That tells us that we're going to look like something like this. Also, this number is positive, so we're definitely going to have the end behavior looking like that. We would try to factor this. How I would factor this is I would factor by grouping. I would group the first two. I'm going to put plus negative here and group these two and take out a greatest common factor. Notice that you can take out a 2x squared here, and you get 2x plus 5. And then if you take out this 2, you'll get 2x minus 5. Oh, and then we have a minus here. So we can take out a negative 2. And then we'll have 2x squared minus 2, 2x plus 5. That's our function. And we can factor this piece a little bit more by taking out a 2. And we'll get x squared minus 1, 2x plus 5. And then one more step, we can factor that. So 2x minus 1, x plus 1, and then 2x plus 5. From here, you can figure out your roots. You can see that you're going to have a roots of 1, -1, and -5/2 if you set this equal to 0. They all have multiplicity of 1. Because of that, you're going to cross the x-axis for each one of these. I can sketch this really quickly. So we're going to go through 1, -1, and 5/2 is 2.5. We know that the end behavior looks like this. And we know that we're going to cross each one of these. So we're going to look something like this. Now we ask ourselves, how many turning points can we have? Because this is an x cubed, we can have a maximum of 2 turning points. So your graph is going to look almost identical to this one. Put it in the graphing calculator at desmos.com or any other graphing calculator you find. You can put it in handheld graphing calculator, and you should have something that looks just like this.